So what we're going to do here is kind of switch the order of the calculation. So what we've been doing so far is the idea of given a cutoff value or multiple values, which when I say cutoff value, that means the values that land on this number line here. So if we have a normal curve, we cut off there. So like for this case, we had cutoff values of 1.3 and 2.23. So there are these cutoff values that kind of define the area. So what we're doing in those examples was given some cutoff values, we were calculating the area. Because by calculating the area, we found probability or percentage. So this is great for calculating those probabilities or percentages, but what we're going to do is kind of switch the order. What if we knew the area? What if we knew our probability or percentage and we wanted to find the cutoff value? And that's what we do right here. So this is what we did in the past. This is what we're going to do right now, is the idea of given an area, we want to find the cutoff value. And in terms of GeoGebra, it's going to be in the same location. It's going to be very similar methods. We just plug in things a little differently. Some wording that's going to come up in this section, term percentile. If you see percentile, that always means area to the left. Always to the left. So right here, the picture, this is showing us the 70th percentile because it's this cutoff point that separates this lower 70% with the upper 30%. And this terminology is used in the real world. Like if you do any sort of testing and you test really well, they'll tell you like you're in the 95th percentile, telling you that you're above 95% of the other people that took the test. So you're going to tell how far above everything else you are. So to find this value, the idea that we know we have the 70% to the left and this upper 30%, and what we want to do is find x here. So cutoff values are x values. So we knew our x values before, and then we wanted to find our area. Now what we're going to do is be given this percentage or this area, and we want to find our x value. We want to know where are we landing on this line here. So in terms of GeoGebra, we're going to set it up the same. We have our mean, we have our standard deviation, and depending on the scenario, we plug those in to match the question that we're answering. Then, where we edited over here, before we edited in this section because we knew x values, but now we don't know x. Now we know the area, we know the percentages. So if we wanted to find the 70th percentile, and where it says 0.75 here, what we've done is actually plugged in 0.7. So in this section, we're going to be plugging in on the right-hand side of the equation, because we know the area that should be showing up. And again, you just want to make sure you're selecting the right spot to make sure it's going in the right direction. So for this picture, we'd have this to calculate to the left, and then we'd plug in our 0.7 here, and then this value is going to adjust. So let's look at some examples using these ideas. So we're going to continue with rainfall in Portland, mean of 40, standard deviation of 8. So for all of these, in GeoGebra, you'd want your normal curve, and 40 for the mean, 8 for the standard deviation. So I'm just going to quickly fill those in there. So this first one, you want the lowest 10% of rainfall, or this is the idea of the 10th percentile. So what we want to do is have 10% of the data to the left of some cutoff point. So I want some cutoff point, 10% left is going to be a small area, so maybe I'm about here, just estimating there. So we want to know what this value is, but what we do know is that to the left, we have 10% of our data. And with that comes that there's 90% of the data to the right of it, so you can use that complement rule. So what I would do in GeoGebra, I'd have my mean and standard deviation in there. I'd want to find P of X less than or equal to, and then this part, I wouldn't plug anything into GeoGebra because I don't know what value goes there. Then where we have our equal sign, over here, I know that if X is less than or equal to this number, the probability should be 0.1. So we'd plug in that 0.1 into GeoGebra, and then what it's going to do is adjust this value right here, and it's going to say this has to be a 29.75. So the probability notation, again, you edit on the other side of the equal sign, and this means the lowest 10% of rainfall is below 29.75 inches. So that's that first example. For the highest 5% of rainfall, so this would relate to the 95th percentile. So now we're cutting somewhere out here such that there's 5% above to have that highest 5% of rainfall, which forces a 95% to the left. And with each of these, there's two ways to go about it. In that here we looked at X being less than or equal to, so in GeoGebra you would have selected that first symbol to make the left tail. However, we could have calculated the same thing by using the right tail symbol. It's just that we plug in 0.9 there instead of 0.1. So you just want to make sure it matches in terms of direction and percentage. So for this one, what we could do, if we wanted to keep with this 0.05 being the highest percentage, we want this right tail. So for this one, we'd use the right tail button. So that would force us to look at probability of X being more than or equal to, and then we don't know what that is yet. Then on the other side of the equation, we know that that should be a 0.05. So if we plug that into GeoGebra, it's going to be a 53.16. So that would mean the highest 5% of rainfall is above 53.16 inches. But again, we could have done the same thing if you had used the left tail button, so you'd have probability of X being less than or equal to, and over here you would plug in that 0.95. It'll give you that same 53.16. So, for these questions where there's a middle 50%, which in terms of our options in GeoGebra, that makes us want to use this button. But what you'll notice is if you press this button in GeoGebra, this side of the equation locks. Doesn't let you play around with it. And it's just because having 50% trapped between two values can actually happen anywhere. Here we're talking about a middle 50%, but really out here we could be between two values that would be giving us 50% in the middle. So you have to get kind of tricky with this one. So we want to find this middle 50%. So we're going to have some lower value and some upper value such that we'll have 50% right in the middle. So what we'll have to use is, if there's 50% in the middle, what's in the two tails? And it's all symmetric, so there would be 25% over here and 25% over here. So we want to find these two X values. Let's call this X1 and this is X2. And in between is going to be 50%. But again, we can't just go directly to that within GeoGebra, so instead we need to find these individually. So let's look at X1 first. If I just kind of cover that up, we're working with this curve with a mean of 40, standard deviation of 8. And if it has to land right here such that 50% is in the middle, what lines up is that there should be 25% to the left of it. So to find that same value, what what we'd want to do in GeoGebra is find the probability of x less than or equal to, so we want that left tail, and then we don't know what the value is, but to be less than or equal to that value, there should be an area of 0.25. And GeoGebra is going to give us 34.6. And that would be our x1 value. Same thing for our second x value, in that we would want to use this fact that there's 25% of the data above. So we would want to go probability of x more than or equal to, so for this one we're using the right tail button, and having 0.25, and that's going to make a 45.4, which will be our x-dim. So with our calculations, if you have a middle percentage, you need to use the tails in order to find the two x values. So the middle 50% of rainfall is between 34.6 and 45.4 inches. So what I'll do is there will be a technology video where I go through these examples showing the steps through GeoGebra.